Okay, cool. So now that we've gone over all of the answers to the exam, let's begin talking over any other specific problems that you have. I'm just messing with that.
I was like, oh. Okay.
Sorry, that was. I have a bad sense. No, it's serious because you guys came. I'll just give you the answer key later. That's what you guys want to go over.
Can we go over the P and C one?
The which one?
I forgot what it's called, but it's the one with like given the chances or the observed one.
So the posterior probability.
Yeah, that one.
Okay. All right. So what is the equation for posterior probability?
It's P.
Yep.
And wait, did I write down? Parentheses C given observed.
We're off to a solid start here. All right. Probability of what? Is it C given out?
Yeah. And then
Is equal to
PC times P given C over PC times PO given NC plus PC times PO given C.
Okay. Good. All right. Cool. So remember that the point of this is that when we add new information to a situation, sometimes we can adjust the predictions that we're making. And so the way in which we applied this was when we had a family theory that we were able to predict that a certain individual had a particular probability of being carried for a disease, and then we found out some information that was extra to the problem because they had some unaffected children. And so that was allowing us to adjust our prediction of whether or not they were carried. So this formula, I mean, I think it looks kind of intimidating, but it's really not that. If you treat it as a way of, well, first of all, if you can just define what C and O and NC are, and then just kind of read it, like, instead of saying PCO, read like, it's the probability of whatever C is given O, and it'll make more sense. So let's, yeah, you want to do this example? You want to go through that one again?
Lecture 2.
Yeah, let's do that. All right, so let's see, we have our individual of interest.
Yeah.
Okay. So let's start with this. So first of all, tell me about this disease. So what do we know about it?
There's hemophilia. It's recessive.
Okay, so it's recessive. Do we know anything else about it?
X-linked.
It's X-linked recessive. Good. So that means that we're going to see it in males that are heterozygous for that mutation. And we're not going to see it in females that are heterozygous for that mutation, although they can be carriers of that. Of course, females that are homozygous for an X-linked recessive mutation can, of course, show the phenotype. Okay, so if we knew that this is an X-linked recessive disease, and we're seeing it cropping up in this male, what does that tell us? Is this mother carrier or not?
Yeah.
Okay. She's a carrier. Is she homozygous for that mutation?
No.
Why not?
She is not expressing the disease.
Right, so she doesn't have the phenotype, but she has this son who's affected, so that means that she must be a carrier. So that's why we can fill in that dot there. Remember that that dot refers to X-linked recessive mutations. If it was autosomal, then we would see something like this. And half of it would be shaded like that. Okay, so she has this son who is affected. What about her daughter? Is her daughter a carrier of the disease?
No.
No, she's not. Is she a carrier of the allele? Okay. And why do you think that she is carrying this allele?
Is it from the mother?
Oh, okay. That is the source of it. But what? So the mother is heterozygous, so she could have passed on a good allele.
She's having two affected children.
Right. So she's having affected children. So that tells us that this individual is also a carrier because she's having affected males. So the question that we're asking here is, what's going on with this individual? What is the probability that she is a carrier? Because her mom is heterozygous, and so her mom could pass on the good allele, or her mom could pass on the bad allele. So, what's the probability that she is a carrier, based on what we know here?
Wow.
Do you guys all agree with that? Yes. So if this mom is a carrier, so she's not homozygous for mutation, she's not homozygous wild type, she's heterozygous here. The question is what is the probability that she is going to pass on this bad mutation to her daughter? 50%, right? Because she can either pass on this allele or this allele. And so it's 50%. So the probability that this daughter is a carrier is equal to 0.5. So, and that's where we would be if that's all we knew about this problem. Okay? Because we could just say, okay, that she has a 50% probability of carrying this. But then she goes on to have, there's additional information in this pedigree. And that changes our ability to predict whether or not she's a carrier, because she goes on to have two sons who are unaffected. And so that changes our ability to predict what's happening here. So let's rephrase this a bit. Okay, let's say that C is equal to that this individual is a carrier. So she is a carrier. And so NC, she's not a carrier. Okay? Because NC is not C. Okay? So she is not a carrier. All right. What are we observing? So remember I said that there's new information here? Okay. What we're observing are two unaffected children. Is that clear? So that's the new data. So remember that Monty Hall problem? You know, Monty has opened one of the doors and shown us that there's a goat behind there, and that's changing the probability that the car is going to be behind the door that we chose versus the other door. So we have this new information. Monty Hall has now opened this door. We see that they have two unaffected sons here. So O is two unaffected sons. All right. So now if we read something like this, we're saying probability that she is a carrier. So PC is the probability that she is a carrier. And we already decided that was 1/2. Okay. So the probability that she is not a carrier is 1/2, right? She could have gotten a big allele from mom. Now, the harder ones. The probability of observing two unaffected sons if she is a carrier. Okay, this is going to be the hardest part of this problem. So if she is a carrier, we're assuming that she's heterozygous here. What is the probability that this son will be unaffected? Oh, now I'm hearing some mixed replies here. Okay. Here's her genotype. Big A, little a. All right. What are we going to get from dad? Big A, big A. So big A, little a crossed to big A, big A. So they can have two types of children, either big A, or big A, little a. And remember that in this case, what we're really talking about is a sex-linked mutation. So all they're getting from dad is either the big A on the X chromosome. So maybe it would help if I wrote it like this. Let's write it like this. X A and X little a crossed to dad, who's X A and Y. That's probably the better way to write this out. And so we can have either X big A from mom and X big A from dad. Or we can have X little a from mom and X big A from dad. These are girls. Or we can have X big A from mom, Y from dad, X little a from mom, Y from dad. So we know that these are boys, not girls. And so what's the probability of being an unaffected male, which is this case right here?
Did you multiply these two?
What's that? It's half. It's 1/2. Okay. So we're not asking what's the probability of having. We know the sex of this individual, right? And so we know that this male could either be affected or unaffected. So we're not going to say the probability of. If we didn't know the gender of this, we'd say, okay, the probability of an unaffected male would be 1/4. But here we're specifying it's a male. All right, so the probability of an unaffected male is 1/2. Okay. What's the probability of having an unaffected male? Again, 1/2. We're just rolling the dice again. These are independent events. And so the probability of having 2 unaffected males is 1/4, because it's 1/2 times 1/2. And that equals 1/4. Good. All right. And now the last one. The probability of observing 2 unaffected sons if mom is not a carrier.
Zero.
100%. Okay? So the reason it's 100% is because if she's not carrying that bad allele on her X chromosomes, well, then the males aren't going to get it. So all of the males will be unaffected 100% of the time. So are you with me on that? Okay, so now that we've calculated these 4 terms, which again, if you just read it, probability of O of 2 unaffected sons, and then remember that this sign here, that up and down sign, that means given that. Probability of 2 unaffected sons given that she is not a carrier. You know, read it out, it should make sense. All right, so now we just plug these things back up into this equation you get. So the probability that she's a carrier given that she has 2 unaffected sons is equal to 1/2 times 1/4. Fine, we can do fractions. 1/2 times 1/4 over 1/2 times 1/4 plus 1/2 times 1. And so that gives us 1/8 over 1/8 plus 4/8, which is equal to 1/5. That makes sense. So originally we thought that the probability that she's a carrier was 50%. But now that she had 2 unaffected sons, we're modifying that to say it's actually 20%. So what happens if she has more unaffected sons.
Less likely.
Okay, it's good. This is going to continue to drop. So if she has 1 million unaffected sons, you're going to become really confident that she's not a carrier. Okay? But if she has a single affected son, what's the probability that she is a carrier?
If one isn't affected?
So let's say that she has 10 unaffected sons, but then the 11th one is affected. What's the probability that she's a carrier?
100%.
That's right. She must be a carrier in order for that son to be affected. So that changes everything. All right. What if she has unaffected daughters? Does that add anything to this problem? No. The daughters are uninformative here because they're not going to be getting another copy of that mutation from dad, and so there's 0% chance of getting daughters showing the disease trait. So it's only the sons that are informative in this particular problem. So does that make sense for posterior probability? Okay. Now what would you like to talk about?
What's that the name for it? I know it's like the progeny phenotypes where you have two parents of certain genotypes, then you cross them with a tester. You're trying to figure out like the order and the distance they are.
Okay. Do you have a specific example problem that we can use?
Yes.
Is that one of the book problems?
This one we used in our discussion.
Okay. So you want to go over that again?
Yeah, sure.
Okay. Let me just write down the basics for it. We'll fix that. Let's see. So this is. Okay. So we started off with flies that are B plus, B plus. So those are the vestigial wild types. We have the curly wing. Or was that something different? Doesn't matter, it's just a symbol at the end. CT, Alright, so these were crossed and produced F1, and ultimately that is crossed to a started off with 2 parent flies. One of them had this curly wing and what is CT again? We don't know. So it's CU, CT. These are the mutant forms of the allele. And then we have a fly that is mutant for vestigial, and it's wild type for curly wings, and I don't remember what CT is. Anyway, so they produce an individual that is heterozygous, okay? And so we would have gotten 1 chromosome from one parent, and it would have gotten the other chromosome from the other parent. Right? And then, so this individual is heterozygous. We'll put dots between these really instead of this line. And then this was crossed to a homozygous recessive individual. That is I'll stick with that way of writing it for now. Okay, and so this is a 3-point test cross. So if you do a test cross with one locus, which would be, say, big A cross to little a, what are the ratios of the progeny classes?
3 to 1.
What's that?
3 to 1. No, 1 1.
1, right? So 1 to 1, where we end up with big A, little a, or little a. Remember? And the contribute, yeah.
For that one, we cross with the tester, right? Which is like all recessive. Is that
Which is
what?
what?
All recessive. The tester.
Yeah. So this is the tester right here. So the tester is going to be homozygous recessive for the loci of interest. And so when we have that case, we're going to have 1 to 1, big A, little a, or little a, right? So that's a very clean and easy to observe ratio. What happens if we have 2 loci? Okay, so say we have big A, little big B, little b, cross to little a, little b. What types of progeny classes can we observe? Let's assume that these are independently segregated. How many classes will we see? 4. Right? And the ratios will be 1 to 1 to 1 to 1. Okay. And the reason is that we can get either the big A or little a from this parent, or we can get either the big A, the big B or little b from this parent. So think about the gametes that this parent can produce. It could be big A, big B. It could be little a, big B. It could be big A, little b, or it could be little a, little b. Those are the 4 possible gametes that this individual can produce. This individual only produces one type of gamete, right? So they only produce little a, little b. And so what that really means is that all the interesting stuff is happening here. That's the beauty of the test cross, is we can ignore whatever's going on here because we've got this homozygous recessive background. They're always going to produce the same gamete. It doesn't matter if there's a combination happening or not. We don't observe it because they all end up phenotypically the same. And the other cool thing about the test cross is because you're doing this against this recessive background, whatever phenotypes we observe here are determined by the genotype of the gametes contributed from this parent. All right, so 1 to 1 to 1, where we end up with big A, little a, big B, little b, or little a, big B, little b, or big A, little a, little b, or little a, little b, little b. So these 4 equally abundant classes, if they're segregating independently. And again, the phenotypes of these individuals will be solely determined by whether they got the big A or the little a, or the big B or the little b allele from this parent. All right. So when we go to this 3-point test cross here, how many progeny classes are there? 8. And if they were independently segregating, they would all be equal in a 1 to 1 to 1 to 1 to 1 to 1 to 1 ratio. I'll check that later to find out if I counted the right number of ones. Okay, so what you're noticing there is a pattern where we're going like to the n, where we're talking about n loci. So this is one locus, so we have 2 possibilities. Here we have 2 loci, so that's 4 possibilities. 3 loci, that's 8 possibilities. All right, so we have 8 possible genotypic classes. And if these were on 3 different chromosomes, then we would expect 1 to 1 to 1 to 1 to 1 to 1 to 1. And life would be good. But so in this problem, we're asking whether there's linkage going on between these loci. And if there is, then what's the distance between these loci, and can we put them in order? Right. So here we have our 8 classes of progeny. And we only wrote down the genotype that came from this parent, just because it's a little bit easier to read. And remember that the phenotype of these flies is determined solely by the genotype of the gamete that was given by this parent. This one might as well be invisible. Okay, so we're clear on that? Okay. Did I get these genotypes correct here?
Yeah.
Sweet. In some of the problems you may have seen that they just write plus instead of like CU plus. I just made it all like CU plus so that we can be specific about which things we're talking about. Whatever works for you. And in the end, if you want to say like, let's make V into A, and this into B, and this into C, and it helps you to work through things that way, whatever. Okay, just keep it straight. So we have 8 classes. And what you'll notice is that, remember that this parent is heterozygous for all 3 of these loci? That's what makes this interesting. What you should see are 4 pairs of progeny. So, and these pairs will have approximately equal numbers. So this stands out as an obvious pair. And so what makes this a pair is first of all, they have approximately the same number of individuals in that class. And second of all, you'll notice that amongst these guys, we have all the alleles that were present here in this parent. So, okay, if we're V here, then we have to be V plus here. If we're CU plus here, we're CU here. If we're CT plus here, we're CT here. So there's, remember that when these crossover events occur, we don't just produce one type of crossover, we're affecting 2 chromosomes, right? Because we're swapping information between those 2 non-sister chromosomes. So it makes sense that we're going to see approximately equal numbers of these things. And so we wouldn't see like V plus CU plus and CT. That wouldn't make any sense, because I'd be like, well, where did all the CUs go? So again, here we have another pair. And again, we can see that we have 3 mutant alleles, 3 wild type alleles. Here we have another pair, and we have 3 wild type alleles, 3 mutant alleles. And here we have our last pair with, again, 1, 2, 3 mutant alleles, wild type alleles, and 1, 2, 3 mutant alleles. So everything is good. It's not just that the numbers are similar to each other, but we also have, we've conserved the alleles. All right. So we talked about this before that because crossovers are happening at some proportion of the time, but not all the time, we're going to expect that the parental genotypes are going to be the most prevalent. So this class that produces all of these individuals, this is our parental class. Which is to say that these gametes, the chromosomes that were present in these gametes preserve they're the same chromosomes at these locations at least, that you would have seen in this parent. Does that make sense? Mm-hmm. So these alleles all stuck together just the way they were in this parent. There wasn't a crossover event just to start scrambling them up. And then there's our least common class here. which is by far the least. And if getting one crossover event is uncommon, what's even more uncommon is getting two crossover events. So these are our double crossovers. And then these are classes where one recombination has taken place. All right, and so you're with me on this. All right, so how do we know which gene is in the middle? I'm going to tell you a little trick right now, which I did not cover in lecture, but it is in the book if you read it. Okay, so one trick to know which gene is going to be in the middle is to say, well, okay, if these are the parental chromosomes, they look like, and again, we don't know the order here, we just know it's this allele combination. If these are the parental chromosomes, then we're asking, how do these compare to these double crossovers? So here we have VCU plus CT plus. Here we have VCU plus CT. CT switched. Okay. Same thing, V plus CU, and here we have CT, here we have CT plus. So CT switched. The locus that switches between the parental class and the double crossover class is the one in the middle. So just looking at that, we know that the order is going to be V, CT, CU. So you look for, well, most of it should be the same, but there's going to be one that's going to switch. And hopefully that makes sense why that is. So if we have A, B, C, A, B, C, okay, in order to, so if we have a double crossover event, so we go here, and then we go here. C's are terrible. They look like, little C's look like big C's. Okay, so here we have little a, big B, little c. Here we have big A, if we go that way. Little a, big A, little b, big C. So what were the parental chromosomes? They were little a, little b, little c, or big A, big B, big C. And notice that B, which was in the middle, switched in that double recombinant group. Okay. Does that make sense? Okay, so that's the quick way to know who's in the middle. But we want to calculate map distances between these loci. And so what we're looking for is if we want to know the map distance between V and CT, well, we need to find out where recombinations occur between V and CT. So what that means is that for the moment, ignore the CU locus. Just block it out of your mind. It's gone. And just think about V and CT. So if the original parent genotypes were V and CT plus, or V plus and CT, then what represents a crossover between these? What genotypes would represent a crossover? So imagine that this is one chromosome and here's the other chromosome. Right, okay, so the recombinants would be V and CT, or V plus and CT plus. Good? So we've done a crossover here, so V and CT, or we've done a crossover here, V plus and CT plus. So those are recombinants where we've now changed the allele combination. So all we need to do is count up all the situations in which we see this genotype combination. So we look for which individuals have V and CT. Here, so that's 89, plus here, 3. Which individuals have V plus and CT plus? 94 and 5. Okay. And so then we add all these up and we get sorry? 191. Okay, so we had 191 individuals that represent recombination between these two loci. But we're interested in frequency, not the actual number. And so in order to get the frequency, what do we have to do?
Divide by the total.
That's right. Divide by the total number of individuals, which is
1.4.
1448?
Yes.
1448, okay. And so what do we get?
13.19.
13?
1319.
13.1.
I'm sorry.
1319.
1319? Okay. So let's say 13.2 centimorgans, or 13.2% crossover. Yeah.
Did you want it in that form on the test?
What?
Or, like the centimorgan?
You could, if you were writing map distance between.
Like if we were to
B and
put
C.
.1319 on the map, would you like deduct points?
I would like to see you express that in terms of map units or centimorgans.
Okay.
Yeah. Because if you just wrote .13.
So you want units on here, obviously. Just making
Yeah,
sure.
right? I mean, 'cause how do I know what you're talking about? Like, you could be talking about percentage or map units or centimorgans, depending on, and so you could be saying 0.13 centimorgans, which would be way off, right? So I think it's always best to clarify the units of what you're talking about. Yeah. Okay, so 13.2 centimorgans. Let's repeat that process between, say, CT and CU. So first off, look at what the parental genotypes were. So CT and CU is always double, they're either both wild type or they're both mutants in the parental class. And so we're looking for instances where we have this combination or this combination. And so, yeah, so we can do this group, so 45 plus 40, and then there's this group. Here, plus 3 plus 5. Right. What about this class? Not recombinant. Okay. So we can add this up, divide by the total population size, and we're going to get the distance between CT and CU. Awesome. So what happens if we do it for V and CU? Say you don't remember my trick about who's in the middle. Okay, we can still do that because we can go, okay, who's between V and CU? We can look for the recombinants and add that up. The trouble is that when you do that, you're going to pull out, okay, this group and this group as being recombinants. But you're going to get a map distance that is not quite the distance that happens when you sum up this map distance and this map distance. And the reason for that was that in the double recombinant class here, we weren't noticing that there was double recombination happening between V and CU. Because V, CU plus, V, CU plus, V plus CU, V plus CU, it's the same, right? So we ignored that when we were initially calculating this. But in fact, now that we know the gene order, we know that when we swapped CT here, there was actually 2 crossover events that occurred. And so these need to be included in that calculation in order to really know the distance between these 2 loci. Right. And so, and these count for double. So we would do 45 plus 40 plus 89 plus 94 plus 2 times 3 plus 2 times 5. That's the number of crossover events that occurred for that particular group. In the end, the point is that the distance between here and here and the distance between here and here can be added together to know the map distance between here and here. Does that make sense? Now there was a homework problem that talked about taking map distances and then predicting what different genotype classes would be. Did you guys get that one? There is a problem about Mr. Spot. There was also a problem that dealt with, it asked whether or not two loci were linked. So it did a 3-point test cross, but you were asked to look for whether or not there was evidence of that all of the loci are linked. So let's deal with that's this situation I'm talking about right now. So say we have so say we were doing this 3-point test cross, and this is going to go horribly awry because I'm making this up on the fly. So let's see what we can do here. So let's say that we cross these guys, we get progeny classes that represent. It'd be really good if I use an example. Probably best if I use one of the examples. Okay. Let me find it real quick. It was just was this number 49 maybe? Yeah, one of them where there was only linkage between two loci but not between all three.
49. I have it. 49.
Was it 49?
Yeah.
Okay. Do you want me to go through that problem? Or do you guys understand that?
Sure, let's go.
Let's go over it. It'll probably work out better than just string this up. So okay. So problem number 49, we're talking about mice that have these. Big W is waltzing.
What chapter is this from?
This is chapter 4, I'm sorry. Little w is non-waltzing. Big G is gray, and little g is albino. And big B is bent tail, and little b is straight tail. And so then we got this table of different progeny classes. So we have, for instance, and so this they had an individual that was heterozygous for all three loci. Is that correct? Yep, okay. So an individual that is presumably heterozygous for all three loci. It's crossed to a homozygous recessive individual. And then we got the following phenotype classes. So waltzing, gray, bent. We'll just write W, G, B. We have, there's 18 of those. We have waltzing albino and bent. Waltzing albino and bent. We have 21 of those. We have non-waltzing, so little w, gray, straight. Oh, I did this wrong. 18 of those, non-waltzing. Okay. So we had the following phenotypic classes. So the first thing that we had to do was convert them from those phenotype classes to writing out some gene symbols here, so that it makes sense. And we were asked to determine how these loci are connected to each other, what the distance is between them, whether or not they're all linked. And so looking at this problem, okay, we do see 8 phenotypic classes. That's to be expected, but that's going to happen even if we have 3 loci that are completely independently sorted. So that's not unusual. So the first step that we've talked about doing is ranking these things in terms of frequency within the progeny population. And so this is done here relatively, where we have these classes are most abundant and then these are least abundant. But what's different here than what happened in the last 3-point test cross that we talked about? Hmm? What do you think is different?
Ratios relatively close to each other.
Okay.
Tell which is correct.
I'm sorry?
Can't really tell which is correct.
Yeah. Well, that's kind of hard, right? Also, we can't really tell if there's a double recombinant class in here. So that makes things a little bit challenging. Normally, I would look at a table like this and I would say, okay, here's the parental class, here's the double recombinant class, and here are the single crossover classes. Okay. But here it's like, well, what is the parental class? I don't know. And also, there's no obvious double crossover class. And so that should be our first clue that something unusual is occurring. And so, yeah, what it looks like is we have, this group and this group, where these are more frequent than these, but that's about all we know. We're not seeing all those pairs in the same. So, what do we do with this? What does this mean is happening? So I think what you can do is you can look at if the parent was heterozygous, it's going to have big W, little w, big G, big B, little b, and then the other parent was homozygous for little w, little g, little b. Let's look at possible combination between WG and start there. Remember, we don't know exactly what the parental chromosomes look like because nothing's really standing out as like a very abundant class. And so let's just consider all possible situations. And so we could have big W, big G. We could have big W, little g, little w, big G, and little w, little g. And let's see how frequent these are Okay, so for this we have, so we have 18 here, we have big W little g, 21 here, we have little w big G, 19 there, little w little g, 22 there. And then we have some more here. We have some more here. And here. And here. So we end up with 22, 26, 24, 28. What does that look like to you? Yeah, it looks like a 1 to 1 to 1 to 1. So remember earlier when we talked about two loci segregating? I did big A, little a, big B, little b. And we said that if they're independently assorting, what sorts of ratios are we going to see in the test cross? Okay. So are these linked or are they independently assorting? Right, okay. Cool. So we know that W and G are independently assorted. Yes?
Why do we pick W and G again?
I'm just starting somewhere.
Oh, okay.
Yeah. And so now we can repeat this process with G and B. So let's do it with G and B. So we can have, again, big G, big B, big G, little b, little G, big B, and little G, little b. So big G, big B, we have 18. For big G, little b, we have 19. Little G, big B, 21. Little G, little b, 22. G, little b, we have 4. 5, and little g, little b, I'm sorry, 5, 6. Again, we're ending up with that 1 to 1 to 1 to 1 thing. Okay, so we said that W and G are independent, and it looks like G and B are independent. Okay. So what's the last combination that we haven't looked at yet? It's W and B. So let's check those guys out. So now we have big W, big B. We have 18 there, and then there's some here. That's 21. And little w, little b, 19 plus 22 here. So big W, little b, we have 4. And here's another one, plus 5. And little w, big B, we have 5 plus 6. So we're ending up with 39 plus 11, 9, and 31. Aha! Now we're seeing something different. This is not 1 to 1 to 1 to 1. In fact, it's a very different from 1 to 1. This looks more like 3 to 1, 1 to 3, something like that. So what this is telling us is that although there's not linkage between W and G or G and B, there is linkage going on between W and B. So we know that the parent was heterozygous. Do any of these classes stand out as the parental chromosomes? I'm sorry?
Not really, because you have 39 and 21.
Right. But could these be the parental
So
chromosomes?
maybe.
Yeah. So again, we're looking for that obviously more abundant class. And so the parental chromosomes were likely WB and little w, little b. I'm sorry, big W, big B, little w, little b. Note that these are most abundant here. So I really shouldn't say 3 to 1 to 1 to 3 because that's a little bit misleading here. What we want to do is calculate map distance between these things. And these aren't necessarily going to be segregating in a 3 to 1 ratio. It could be 12 to 1. It could be anything. So I was just doing a rough kind of estimate here to point out that it's not 1 to 1 to 1 to 1. Don't think that I'm talking about single locus Mendelian segregation here. Okay? So, let's focus on this. These two are most abundant, and if we look at them together, all of the alleles that would have been present in the parent are conserved. We have 2 wild type alleles, or 2 dominant alleles and 2 recessive alleles. So we couldn't say, for instance, combine these two together, it wouldn't make any sense. That these would be the correct genotypes because we would have no big B around. All right, so what is the recombination frequency between W and B? If these are the parental genotypes, then what are the recombinant genotypes? Okay, these are the recombinant genotypes. And so, once again, to get crossover frequency, we add up the recombinants. So 11 plus 9, and we divide that by the total number. So this all adds up to be 100. And so the map distance between W and B is equal to 20 centimorgans. Yes? Okay. There is no map distance to calculate between W, B, and G because G is segregating independently. G is probably on its own chromosome. Yes?
47.
Sure. From the same chapter? Okay. So, cool. Okay, so in corn, we have 3 loci. And we pass it to this. Okay, and this produces, of course, a heterozygous individual. In this case, we know that these things are located next to each other, so I'm just going to go ahead and write it as big W, little e, big F, and little w, big E, little F. Okay, so we know it's how these guys are sorted out. Okay. This individual we then cross to we do a test cross, so that means that we're crossing to and we're assuming no interference. And we have this map distance between W, E, and F of 8 map units, or centimorgans, and 24 map units, or centimorgans. And we're saying that if we do this test cross here, what proportion of the progeny will be or you can write it however you want to write it. Okay. So which proportion of the progeny will be homozygous recessive? So what do we know? How are we going to get an individual that we know that we're going to get this gamete, or this one, from this parent. So what we're asking is what is the frequency of getting a little w, little e, little f gametes? Does that make sense? How often does this happen?
One in 8 times.
If these were independently segregating loci, yeah. But they're not. But what I'm trying to point out is that this is the question. How frequently do we get this gamete? We know we're going to get this from the tester. The question is, how often are we going to get this? And so for that to occur, we know there's got to be a recombination that's going on between these guys. So if I were to diagram this visual, of course if it's diagram, it's visual. WEF, and on one chromosome we have little w, big E, and little f. The other chromosome, what's it going to take to get this gamete? We're going to have a crossover here and here. So we're going to have a crossover between W and E and a crossover between E and F. Does that make sense? So how often does that happen? Very good. Okay. So we know that crossovers between W and E happen 8% of the time, and the crossovers between E and F happen 24% of the time. So if we multiply 0.08 times 0.24, we should get the frequency of generating double crossovers. However, remember, you're also generating these. You're generating big W, big E, big F. So what is this number? 0.0192. Okay, so that is the frequency of double crossover gametes, but only half of them are going to be little w, little e, little f. The other half are going to be big W, big E, big F. So we need to divide this number by 2. So this is all double crossovers. And the little w, little e class, little w, little e, little f class is only half of those double crossovers. So let's do 0.0192 times 0.5, and that's going to give us this answer here. Does that make sense? And then there's a part B. I assume part B is going to be the tricky one. If the F1 is selfed, what proportion of progeny will be that? Okay. Selfed. So that means that, ignore what's going on here. We're going to cross it to itself. So how are we going to generate an individual that is homozygous? So first off, we agree that we need to generate this gamete. Right? But we also need to generate that gamete again. So if you're selfing it, that means that you need a pollen cell, and you're going to need a female gamete, and you're going to put them together. Yeah, no, let's stand up. and that's how we're going to get this homozygous recessive progeny. Okay, so we need to make the male gamete and the female gamete be little w, little e, little f. So we've already calculated what's the frequency of this happening. What is it? Okay, so 0.0096? Okay. So that's the frequency of getting this. Now we just need to get it to happen in both the male and female gametes. So how often will that happen?
19216.
What's up?
19216 just times
Square.
the square.
Yes, so we're going to take this value and square it. So small number, right?
0.0192.
Point.
Point 0192. This one.
Oh, did I write something down wrong before?
Where's this?
So we did 0.08
Oh,
times
no,
0.24.
Wait. Okay, it's 9.22 times 10 to the negative 5.
Okay, 9.2 times 10 to the negative 5?
Yeah.
Okay. Not very common. So we're taking this 0.0096, multiplying it times itself, and presumably we're getting this number. Any other questions on this?
What problem was this just now?
Hmm?
What problem was this just now?
That was number
47.
47 in chapter 4. Okay. What about you guys in the back? Did you have any particular questions or? You have a question?
Yeah.
All right, bring it on.
It's the quiz 2, like,
Quiz 2.
yes.
Let's refresh my memory. What's on quiz 2?
Like for the discussion quiz.
Mm-hmm. Yep.
First one, part B.
That one.
Do we get partial credit if we,
Let me find the quiz. Cammy was very tricky with that one. So, okay. We had a phenotypically normal woman from Portland who marries a man with a disorder, and they're expecting a child. So we previously, okay, let's start a little bit earlier. We have an autosomal recessive disorder that affects 9% of the population. So autosomal recessive disorder, what is the genotype of individuals that show this disorder?
Q.
What's that? Yeah, so if it's an autosomal recessive disorder, you know, let's say the allele is little a. What's the genotype?
Little
That's
a.
right, little a, little a. Okay, so little a people have the disorder, and in part 1A, we said that 9% of the population was affected. So, is that 9% referring to the allele frequency or the genotype frequency? Which one? Yeah, the genotype frequency. So, you're not going to see the allele frequency with immediately with this autosomal recessive disorder. What we're seeing here are those that show the disease, and the disease is produced by the genotype, not by one allele. So little a individuals are affected, 9% of them, of the population is affected. So that tells us the frequency of little a individuals. So relating this back to Hardy-Weinberg, if we want to say that Q is representing the allele frequency of A, of little a, then we would probably say that Q squared is equal to 0.09, and therefore we could solve this to determine that Q is equal to the square root of 0.09, which is
0.3.
0.3? All right, cool. I should have been able to do that one. All right, so You guys are with me on that?
Yes.
Okay. So now we have our phenotypically normal. Well, the other question that she asked you guys was what percentage of the population is expected to be carriers? So Q is equal to 0.3, then we know that P is equal to 1 minus Q, so that's equal to 0.7. And so going back to genotype frequencies, carriers are going to be individuals who are not showing the disease, but are carrying that mutant allele, so they're heterozygotes. So what is the Hardy-Weinberg 2PQ? There you go. 2PQ. That's going to be our frequency of heterozygotes and carriers, and so that's going to be 2 times 0.3 times 0.7, and then we end up with 42% of the population are carriers. Awesome. So, we have a normal woman, phenotypically. We don't know if she's a carrier or not. And she marries a man with the disorder. So what's his genotype? That's right. He is a little A, little A. They're expecting a child. What is the chance that the child will have the disorder? Okay. So in order for the child to have the disorder, what is the genotype of mom going to be? What's that? Right. Well, she could also be homozygous for it, but then she would show the disease. And we already said that she's phenotypically normal. Right? So yeah, we're asking basically, is mom a carrier? So what's the frequency of carriers in the population? 42%. Okay, so there's a 42% chance that out of the whole population, mom is a carrier. But we're not exactly dealing with the whole population here. So out of the whole population, so let me draw the whole population. All right, we have 9% of the population. These are affected, and these are the little a people. But then we have the rest of this population, which is a combination of big A plus big A, little a people. You agree with me? All right, and let's go ahead and let's divide this up. Okay, so let's say, so we have 42% of the population here is heterozygous. So 42 plus 9, 51. So 49% of them are not carriers or anything. Right? We're good. So the deal is, we're interested in whether mom is a carrier, but we know we're not dealing with the whole population now because we know that she is not affected. And so we can remove that portion of the population here. Let's go on. So now we have, among the remaining population, this is a population now of normal individuals. And among that population of normal individuals, is it 42% of them are big A, little a? No, it's adjusted now because we've changed our population that we're talking about. And so here now it's the 42% divided by the 91%. And that's going to give us our adjusted frequency. It's going to give us the frequency of heterozygotes among this group. So what does that come out to be? 0.46. So 0.46. So really what we're talking about is this 46% chance that she is a heterozygote. And if she is a heterozygote, what is the likelihood of them having an affected child? Let's assume this for a moment. What is it? 1/2. Okay. So we're going to do 1/2 times 0.36. We get 23. You good? Okay. So now, what if she had an unaffected child?
And she's not heterozygous.
Not necessarily. So do you remember the hemophilia problem that we did? Okay. So if we gained new information, so if we said, okay, they had a child, and that child was unaffected, that would adjust our prediction of whether or not mom was heterozygote. In the same way that that hemophilia example did. I'm just getting back to that concept of posterior probability. So say these guys had an affected child. What would we know about her genotype? Is she a carrier or is she not? She's definitely a carrier. And therefore, if they were to have another child, we would now know that there's a 25% chance that that child is going to be affected. Because now we know her genotype, we know his genotype, and forever after we know like what the probability is of those children that are going to have being affected. What I'm saying is they had an unaffected child. We still don't know her genotype, but that piece of information could influence our prediction of what her genotype is. We could use that posterior probability problem to adjust that. Because we know the probability of mom being a carrier is equal to 0.46. The probability of observing, let's say it's one unaffected child. Probability of observing one unaffected child given that she is a carrier is equal to if she is a carrier, how frequently will she have an unaffected child? Half the time. Okay. Cool. The probability that she's not a carrier is equal to what's that? So she can either be a carrier or she can not be a carrier.
Is it not 49?
It's going to be 1 minus 0.46 because she can either be a carrier or not be a carrier. And so so you encompass both of those possibilities. That's a 100% scenario. So we're saying if she's not one, then she's got to be the other. So it's 1 minus 0.46, so that equals 0.54. And now the probability of having an unaffected child, given that she is not a carrier, is equal to, she's not a carrier, can she have an unaffected, can she have?
No.
Affected?
What's that?
Wait, are we trying to find that if she's not gonna have an unaffected
The
child?
probability of having an unaffected child, given that she is not a carrier.
One.
One. Good. Okay. So now we could plug that back in to our posterior probability equation, and we would say 0.46 times 0.5 divided by 0.46 times 0.5 plus 0.54 times 1. That would give us
Point 2987.
0.299. Okay. Okay, so now we've adjusted the probability that mom is a carrier from 46% to 30%. So it's gone down because she had an unaffected child. And so we could say, given that she had one unaffected child, what is the probability that her second child will be unaffected?
Divide by 2.
I'm sorry, this times what?
No, wait.
Oh,
What's your question again?
So we have unaffected mom,
Yeah.
and we have they have one unaffected child. What I'm asking you is, what is the probability that this second child, they have another child now, what's going to be the probability that second child will be affected?
0.15.
0.5.
1.
It'll only be 0.5 if she's a carrier, right? And what did this tell us? This is the probability that she is a carrier, given that she had this one unaffected child. So remember, it's the same thing as what we did before. We said, oh, there's a 46% chance that she's a carrier. So therefore, if she is a carrier, there's a 50% chance that they're going to have an affected child. So, so now we know that there's a 0.9% chance that she is a carrier. And so there's divide that by 2, and that's the chance that she's going to have an affected child. Does that make sense? Because all we're doing is we're adjusting the prediction that she is in fact a carrier.
You said divided by 2?
Well, right, because what we're saying is like, so if we assume that she's a carrier, and really there's a 29.9% chance that she is a carrier. If she is a carrier, how many of her children do we expect to be affected? 50% of them, because it's going to be big A, little a, crossed to little a, little a. So that's just an example of how you can take an extra piece of information and adjust those predictions. Any questions on that?
What was the last step we just did? We multiplied?
I'm sorry, so you remember before we said we thought there was a 46% chance that she was a carrier, but then we went through all of this now that we knew that she had one unaffected child, and we said that now there's really about a 30% chance that she's a carrier. The same thing applies though, where we're saying if we're interested in the probability that she's going to have a child with this disease, it's going to be 50%. It's going to be 0.5 times the probability that she's a carrier. So again, it's going to be 0.5 times 0.299. And so it's going to be about a 15% chance of having an affected child.
Okay.
Or an 85% chance of not having an affected child. I can stay a little longer if you guys have any extra questions. But you're good.
You're doing a Scantron, right? So,
What's that?
the Scantron,
That's good.
calculator, pencil, and
Yep.
cheat sheet.
Non-communicative calculator.
No. What, this kind of calculator?
That calculator is fine.
Oh,
And cheat
Wait,
sheets.
those can't talk to each other now, can they? Other than the wire that you then transfer all your little programs.
I don't think so.
I've heard like one calculator can do that.
What's that?
I've only seen like one calculator can split it up before.
They can, like, wireless transfer.
Also put a camera on too. It's very like tricked out calculator. The cheat sheet's one side, right?
The cheat sheet is one-sided.
Okay.
And you guys will turn that in at the end of the exam.